All right, let's talk about CUDA. If you work with GPUs, I'm willing to bet you've had a moment, or maybe a few moments, where you've just stared at your screen, completely lost in the world of NVIDIA. The names mean 5 different things, the versions never seem to line up, and the error messages, well, they can be super cryptic. So today, we're going to build a mental model to finally make sense of it all.
Ah yes, this one. Does this look familiar? This single line has probably stopped more deep learning models and scientific simulations in their tracks than almost any other. It just pops up and everything grinds to a halt.
And look, if you've ever felt totally baffled trying to figure out what it means or what you're even supposed to do about it, trust me, you are in very good company. It's practically a rite of passage, but it doesn't have to be a mystery.
And that's our promise for this explainer. We're going to cut right through the confusion and give you a simple framework and 2 golden rules that will let you look at these problems and know exactly what's going on.
So where does all this confusion even come from? Well, it really starts with the word CUDA itself. It kind of has an identity crisis because it doesn't just mean one thing, not even close. Seriously, think about it. When someone says they're using CUDA 11.8, what are they actually talking about? Is it the compiler, the library, the driver on their machine? What is it?
The answer, crazily enough, is yes. It could be any of those things. CUDA is the name for the entire compute platform. It's the name for the GPU's instruction set. It's the name of the C++ language extension you code in. It's the name of the toolkit you download, and it's the name of the runtime library that gets packaged with your application. And this overloading of the term is the real source of so much pain.
And it doesn't stop there. The word kernel gets the same treatment. For most of us, a kernel is the core of an operating system, right? The Linux kernel, the Windows kernel, it runs on the CPU. But in the CUDA world, a kernel is just a C++ function that you write to run on the GPU. Same word, 2 completely different concepts.
And finally, there's the driver. This isn't just one thing either. It's really a package deal. You've got the super low-level part that lives inside the operating system, and then you have a higher-level library that our applications actually talk to. So just remember, the driver is a 2-part system.
Okay, so how do all these different pieces actually work together? Well, the best way to see it is to follow a single command on its journey from your application all the way down to the GPU hardware. It all starts up top, in your app. Let's say it's PyTorch. You make a pretty simple request, like, hey, allocate some memory on the GPU for me. That request first hits the CUDA Runtime API. Think of this as the friendly, easy-to-use front desk. The runtime then translates your simple request into a more complicated, low-level command for the driver API. The driver API then talks to the actual OS kernel component, which is the only thing that can give the final instruction to the GPU hardware itself. It's a chain of command, flowing from high-level to low-level.
Now, this whole layered system brings up another really important idea we have to get straight: the huge difference between what you need to build an application and what you need to run it.
You know, you can think of it like building a car versus driving a car. Build time is when you're in the workshop. You need all your tools, the welders, the wrenches, the whole shebang. For us, that's the full CUDA toolkit with the NVCC compiler and all the header files. But runtime, that's when someone just wants to drive the car. They don't need the workshop, they just need a key and some gas. And for us, that's the CUDA runtime and the NVIDIA GPU driver. And this table just makes that crystal clear. The compiler, NVCC, and all those header files, you only need those when you're building. They're the workshop tools. But to actually run the program, you only need the essentials, the runtime and the driver. And notice that the runtime, libcudart, is the one piece that's needed in both columns, because you have to link against it when you build, and it has to be there to make the calls when you run.
Okay, we've defined the messy terms, and we've mapped out the system. Now that we have that foundation, we can introduce the 2 golden rules that will solve almost every single compatibility headache you will ever have.
The first rule is all about the relationship between the 2 big software pieces, the runtime that's bundled with your app and the driver that's installed on the system. Okay, here it is, and you can take this one to the bank. The driver on a machine must do the same version or newer than the runtime your app was built with. It's because drivers are forward compatible. A brand new driver knows how to handle commands from an old runtime, no problem. But it doesn't work the other way. An old driver has no idea what a new runtime is trying to say. It's like it's speaking a different language.
All right, on to the second rule. This one has nothing to do with software versions. It's all about the actual code that the GPU itself has to execute.
See, when you compile your CUDA code, you can generate 2 kinds of output.
One is called SAS. That's native machine code, hyper-optimized for one specific GPU architecture. It's the fastest you can get. The other is called PTX. This is more like a universal intermediate language. The driver can take this PTX code and compile it just in time for whatever GPU you're running on. So, rule number 2 is simple. Your app has to contain either the exact SAS for the GPU you're using, or it has to contain some of that universal PTX that the driver can work with.
And now for the payoff. Let's take those 2 rules and use them to finally understand those error messages that used to be so frustrating. Here it is again, our old friend. Now when you see this, what does it mean? Let's apply our rules.
This is a textbook violation of rule number 1. The error is literally telling you the problem. Insufficient driver. Your system's driver is too old for the CUDA runtime your application needs. The fix? It's that simple. Upgrade your NVIDIA driver.
Okay, what about this one? This one feels a little more obscure. No kernel image for device.
This is a clear as day violation of rule number 2. It's telling you it looked inside your application for a kernel image, which is just SAS or PTX code, and it couldn't find anything that would work on your GPU. It didn't have the right SAS, and it didn't have any PTX to fall back on. The fix? You got to recompile the app and make sure you're targeting your GPU's architecture.
So, yeah, it's a complicated system. There are a lot of moving parts. But all this complexity, it's there for a reason. That PTX system means that an application you build today can, in theory, run on a GPU that comes out 5 years from now, without ever being recompiled. It's an incredible amount of future-proofing. Which kind of leaves us with one last question to think about. Is all this complexity a fair price to pay for that?